Okay, we'll go ahead and get started. Welcome everyone to the M-Cube seminar. I'm pleased to welcome Ying Pan. Ying is an associate professor in meteorology and atmospheric science at Penn State. She obtained BS and MS in atmospheric sciences from Peking University in China in 2004 and 2007 respectively, and then a PhD in meteorology from Penn State in 2014. Many of you might remember her from her time here as a postdoc in M-Cubed from 2015 to 2017. And then she started as an assistant professor at Penn State in 2017 and was promoted to associate professor last year. So congrats for that. Her research specialty is in atmospheric boundary layers and turbulence with applications to pollutant dispersion, urban environments, and tornado dynamics. The research tools include theoretical analysis, field observational data, and large-eddy simulation. Welcome.
Thank you, Hugh. Yeah, it's so nice coming back here. Yeah, time flies so fast, already 10 years since I came here as a postdoc. And this work, so that I'm going to share today, and can see, first I want to thank my co-authors of this paper. Sam Ray was a master student working with me. He graduated 2022, and he did all the kind of tedious kind of data analysis and try to kind of this canopy array, canopy horizontal array turbulence study, and then also NED. So basically, my PhD work I did at Penn State was almost all about large-eddy simulation. And when I came here to want to do postdoc, I was like, I want to know how to deal with observational data. Then I started working on jets and getting, working together with NED. And you can see we're still doing things together. Yeah, there's still a lot of things, like the jets experiment was done 2007, so almost 20 years, it's 18 years. There's still so many things we don't quite understand. And then today what I'm going to talk about is this turbulence wave interaction, basically internal gravity waves generated by canopy turbulence when it's nighttime, stable condition. And the motivation of doing this work is because we don't quite understand the wave turbulence interaction, even though they're everywhere. And we know they're important, but we don't quite understand it. And what we know is that internal gravity waves, they occur when we have stable stratification. And turbulence, we need some mechanisms to generate it. Mean shear is one mechanism to generate it. And therefore, what we're thinking about is, okay, and if we're thinking about stably stratified canopy flows, what's going to happen is that because we have a canopy and it does absorb a lot of momentum, and we're going to have this maximum mean shear at about the canopy top. And this is what you can see on the bottom figures here, and these are the CHATS data, the canopy horizontal array turbulence study measurements data. And this is the mean wind profile, and you can see the gradient is kind of almost always the sharpest around the canopy top. And on the right, we just calculate the mean shear. You can see kind of a peak, pretty close to the canopy top. So that's how we guarantee we have turbulence there. And then canopy top is also the place where we can have maximum stratification. So if we look at the top figure here, that was also canopy or horizontal array turbulence study measurements. And so heat flux is plotted here, and when heat flux is negative, it's this green line and this blue line here. And you can see it's most negative at about the canopy top. So then what we're thinking about, okay, then canopy top could be kind of a natural laboratory we can use to try to understand wave turbulence interaction. Because First, we expect both turbulence and wave to be able to occur there. And the second, it's pretty close to ground. And that means we can build tower, we can do all kinds of measurements. It's relatively easy compared to you want to fly to upper atmosphere. And then what we will need, so observation, and we also want to explain it theoretically. That's our hope, right? If we can do theoretical explanation, maybe we can also help what's in the upper atmospheric boundary layer, that's kind of entrainment zone. Maybe we can go even to above the boundary layer, and where it's kind of potentially important for like aviation weather, but we don't have kind of, at least we cannot build tower there. And also, when we get observation, and we can also kind of try to do numerical simulation. And that will be another dimension we can push and to try to build good theoretical understanding. So that's what we're thinking about. And then before getting into kind of wave turbulence interaction, I just want to give some background about what are these turbulent motions near canopy top. So basically this layer, we call it canopy-shear-layer. Why it's called canopy-shear-layer? First there's canopy, and then you have sufficient mean shear, right? You have kind of strong mean shear there. That's why it's called canopy-shear-layer. If you just want to have an empirical understanding where it is, it's kind of from the ground to like 3 canopy heights, roughly, yeah. Not always exactly that number, but just a rough understanding. And then this sketch on the right was drawn in this John Finnegan's paper. And this is for statistically stationary, horizontally homogeneous, and neutral flow conditions. So very idealized. And then what will happen is that the top panel shows that we have this inflection point in the mean wind profile. Inflection point means it's maximum shear there, maximum gradient there. And when we have this, and then we can try to relate it to Kelvin Helmholtz instability in the textbook. That's where you see the inflection point. And then for this instability to develop, first the top panel say you give small perturbation, and the second panel say, okay, and there would be this Kelvin Helmholtz rose and to form. And then the third panel here says, okay, after the formation of this Kelvin Helmholtz rose, because it's turbulent, then you're going to have fluctuation in the mean wind direction. And then after you have this fluctuation, and you say this is a row, this is another row, they kind of, when they come close to each other, sometimes they will come close to each other because they're fluctuating. Sometimes they're going to apart from each other, and when they come close, this one is going to push this one up. That's vortex interaction. So vorticity interaction, this one is going to push this one up. This one is going to push this one down. And finally, they form this kind of like a so-called head up and head down hairpin vortices. Like you're going to see this pair. So this is a head up, and this is a head down. So you see the pair of hairpin vortices. And these are like the so-called energy-containing motions in turbulence. So they contain energy, and then their average size is kind of on the order of twice of the integral length scale. And in neutral canopy flow, and like from these papers, like integral length scale is on the order of 3 canopy heights, so twice of integral length scale is about 6 canopy height. So this is basically the background of canopy turbulence. And then, the next thing I want to kind of give some background about is the observation of nighttime canopy waves. So this was actually, to my knowledge, the first paper that I found. It was by Shuhui Li and back to the 1990s. And what happened was that during some nighttime episodes, they observed this type of, this is the velocity component, horizontal in the mean wind direction. This is velocity component, vertical. And these time series on the left, those are temperature time series. And what they see is we look at this, and suddenly we see like the period of these motions are on the order of 1 minute. And then they did the spectral analysis, and here they say, okay, here is a very obvious peak in the vertical velocity power spectrum. It's at about 1 minute. And then they were like, okay, what is this motion though? Because if it's internal gravity wave propagated from upper atmospheric bounded air, it should be on the order of like 8 minutes. So that's what we learned from the textbook. And if it's canopy turbulence, the nighttime, the integral time scale is on the order of like 5 seconds. So it's not close to the upper ABL waves, and it's kind of also not close to turbulence. So this must be some different motion. And they were like, okay, they thought about then what's that? And they said, this must be like internal gravity waves generated by canopy turbulence. Of course, like when they kind of provided this explanation, they say, okay, this scale matches, but whether that is absolutely true, we still don't know. Like this was kind of some preliminary observations. And the more observations was done actually during the canopy horizontal array turbulence study by Shane Mayer. He was also an ASP postdoc here, right? And so he went there, he built this aerosol backscatter lidar, and then at nighttime, they saw these parallel bands of aerosol backscatter intensity. And the wavelengths of these bands are on the order of 3 to 10 canopy heights. And at the meanwhile, they also look at the vertical velocity time series, and they found the period was on the order of 1 minute. And then they made this connection saying, these are the signals of nighttime canopy waves. So this was basically what they observed using a different instrument. Okay, and then they proposed how to kind of explain it theoretically. And this is what they did. First, it's linear stability analysis. So basically what it is, we first write down Reynolds average Navier-Stokes equations. And then we split each flow variable into a base state and a perturbation. And then we remove the base state equation. We also remove the second order, so the products of perturbations. And then we get the linearized equation of the perturbation fields. And then we assume the perturbation is kind of like a wave mode, and we plug it into the equation and see whether it's going to grow or it's not going to grow. And if it's going to grow, what's the growth rate? So this is the equation that we can get. And on this equation, there are these blue boxes. Those are canopy drag and the canopy heat exchange term with the airflow. So those are the canopy effects. And also you'll see these red boxes. Those are the eddy diffusivity of momentum and so the turbulent mixing of momentum and heat. So these coefficients A and K, those are eddy diffusivities. And then what they did was like they did this linear stability analysis, and they tried to identify the so-called fastest growing mode. So like you can impose whatever wave number into it, which one is going to grow the fastest? They believe that's going to be the wave number, or say the wavelength of that fastest growing mode is going to be the wave number or wavelength of the internal gravity wave generated by canopy turbulence. And then they compare that to what they observe in the LiDAR image. So this is what they are doing, like in this plot on the right. So the top one is that, so all these terms in red and blue boxes are not there. So that is the traditional Kelvin-Helmholtz instability analysis. The second panel here, that's the one that they include these blue boxes in the equation. And the third one is that they include blue and red boxes in the equation. And for this eddy diffusivity coefficients, they just assume it to be some median number that they get from observations. And the last one is that they kind of try to tune this eddy diffusivity parameter and to get the best agreement with observations. And what you can see here on the right is like, yeah, no matter what you do, you still have those data points that the theoretical prediction like of the wave number is far above the observation that is above this solid line, which is the 1,219. And therefore, we can see like wave number is kind of overestimated and actually not quite small because, for example, for the bottom one, they really didn't report in their paper about that kind of what the actual final coefficient they got. So if we look at the third one, yeah, it's kind of using a medium kind of value for those coefficients, not kind of giving you. I mean, it does not look bad, but we still have questions, yeah. And say and basically they say like you can conclude that the wave number is substantially underestimated. And when I look at this kind of theoretical framework, I actually have a question about, yeah, why do you believe that the fastest growing mode is what you want? Because if it's fastest growing mode, it's growing. And because it's growing, it's dynamically unstable. Whereas if we think about the waves, by definition, waves are dynamically stable. So first I had this question. And also a second question came up from this other figure in the same paper that is, so they say, these shaded columns are where the wave events, the nighttime canopy wave events, they will occur. And the curves there, that's the gradient Richardson number. And what you can see is that when gradient Richardson number becomes positive, that means it becomes stable, the waves, they don't occur immediately. You will have to have the gradient Richardson number to reach a certain point. So it becomes sufficiently stable so that you're going to see waves. And therefore, that means if you're thinking about the fastest growing mode, you can always calculate it. Does not need your stratification to be sufficiently stable. So that's kind of like a second question that I came up here. And then to kind of try to answer these questions, so we went back to think about canopy-shear-layer turbulence. And if there is stable stratification, what's going to happen on top of that? So here from neutral, I changed the wording to stable, right? That's a condition. And then when it's stable stratification from the Kelvin-Helmholtz instability development, in the textbook, we know there is a prediction of a critical wave number that separates unstable and stable motions. And then the next one, when we look at like this turbulence, basically these head up and head down hairpins, what we can see is that each of them has some legs. And these legs, so the legs, this is a leg, the legs of these hairpins, they are stringwise oriented vertical structures. And what it means is like if the wind goes this way and the vertical structure is also along that way, so it's spinning like this. That means it's kind of, if you look at the vertical motion, it's going down on this side, it's going up on that side. And we all know when we have momentum transport downwind, that means downward, that means U prime and W prime are strongly negatively correlated. So if W prime has this negative correlation, U prime should also have this negative correlation. And something like that. So this is kind of our understanding of these hairpin vortices and their legs. And then, if we think these hairpin vortices are actually the structure that will generate waves, and what we're kind of trying to guess is that, so for this critical wavelengths, if it's greater than the size of these hairpin structures, then these hairpin structures are still unstable, so they are still turbulence. But when these critical wavelengths become smaller than the size of these hairpin structures, that is twice of the integral length scale, then these structures become stable and they become waves. So that's what we're thinking about. And then we just mentioned like these vertical structures, they induce kind of spatial correlation on W prime and U prime. And then we'll say, okay, now we're going to focus on these hairpin structures. We're going to use their legs to kind of try to catch them. And then we propose two hypotheses. So we say, if it's neutral, okay, and then the average lifetime of these integral turbulent structures would be the integral timescale of turbulence. And therefore, if we average turbulence fluctuation W prime and U prime over blocks of integral timescale, and we should see the most clear influence by these legs of these hairpins. And if they're negative correlated due to these hairpin legs, and if we average the signal over blocks of integral timescale, we're going to see a most negative correlation. So basically, this is kind of not time average, but you can see this is wind tunnel measurement. So this is stringwise direction, and the vertical is the spanwise direction. And these contours that's in the dashed contours, those indicates that the correlations of U prime are negative. So you can see most negative correlation kind of here and then here and with respect to the center. Yeah. So we see that in wind tunnel experiment, and we hypothesize that if we average this U prime over time blocks of integral timescale, we're going to see the most negative correlation at this like spanwise separations. So this is the first hypothesis. The second hypothesis is that, okay, what if now these hairpin structures become stable, become dynamically stable? And then when they become dynamically stable, their lifetime should not, their lifetime should become something closer to the buoyancy period. So no longer the turbulence integral timescale. And then W prime and U prime, they should stay in, like if you think about the wave period, the signal will stay in phase on average over half of the buoyancy period. And that means if we block average U prime, W prime over half of the buoyancy period, now we're expect to see the most negative spatial correlation of these signals. So basically, these are hypotheses. And then we're going to see what we're going to get in observations. And what we're going to do is we're going to use this canopy horizontal array turbulence study, because that's in the walnut, is in a walnut orchard field. And there is a horizontal array here, and there is a vertical tower 160 meter to the north of the array, and the array looks like this. So, and basically for to guarantee that we have sufficient fetch of the canopy, because both of them are located near the north border of the field. So we want the wind to come from somewhat from the south. So this is our configuration. And also because you see like all our kind of expectation of these hairpin structures, whatever, from the beginning of our understanding, we assume statistically stationary, horizontally homogeneous flow. And also that those idealized conditions are required for us to really calculate spatial autocorrelation functions accurately. So we need to identify statistically stationary periods first. And then after we have done that, we say, okay, we want the mean wind somewhat coming from approximately the south. So we have sufficient fetch. And then we also want to make sure it's like horizontally homogeneous. And then we want to exclude the periods where the sensors, they observe very different wind directions. So this is our idea, and we want to obtain these idealized periods and to see whether our hypothesis, they will work or not. Yeah, if you're interested in what this kind of statistical method, how you determine statistically stationary periods, it's kind of, I would not say it's difficult. It's not as difficult as large-eddy simulation, but it's still maybe like 2,000 lines of Fortran code. But we can, like, if you're interested in how that was working, we can kind of talk afterwards. But basically, you can see that these stripes are the most non-stationary events caught by this technique, this statistical technique. It was not caught by our eyes. It was caught by this algorithm. And what you can see is that the behavior of the time series here, and the time series here, and the time series here, they actually show some like very different behaviors. And this was, I mean, for now, to save time, I'm not going into all the details, but basically this kind of, these results are kind of encouraging, right? That means our algorithms are not doing something strange. It is doing the right thing. It does tell us where we have the most non-stationary event, and then the rest of them would be stationary event. Of course, what you call stationary and non-stationary, you need to give any statistical method has a significance level. If you're becoming more stringent, you have more non-stationary event, and you have a shorter period, you call it stationary. And we don't go through all the details here, but this was all done by my former master's student. Yeah, he did a great, tedious, but and also he did a great job here. Okay, and now from all these results, we actually have only identified one near neutral period. And we have identified more like unstably stratified period, but only one we can call it near neutral. And then we can see, so these are the kind of separation between sensors. So starting from like 7.5 meter, and then twice of it, and then 3 times of it, and then finally, for the 13.76 meter separation distance, we see negative autocorrelation of U prime. And then this delta t is like we do time block average, and we increase it, the average in time block, it becomes more negative until it hits this vertical dotted line, that is the integral time scale. And then it starts to increase. So that means basically our hypothesis number 1 does work during this one period, even though we only found one period. However, for neutral canopy flow, we can also we also have like large-eddy simulation results. So here on the right, we have this is a current PhD student working with me. He did all these plots and he presented them at the Denver Summit meeting this year in May. So basically, we got so these dots. Black dots are actually from this figure on the left. That's this period D.E from CHETS. And red crosses are the wind tunnel measurements done by Roger Shaw, 1995. The blue crosses are from a large-eddy simulation done by Hongbin Su back in 2000. And then this blue solid line, this was a large-eddy simulation of current canopy that I did. That was in the paper published 2016. That was 9 years ago and still pretty old. And then this black line is the kind of a new large-eddy simulation done by this student working with me. And that's for the CHETS canopy. And basically, this is the, we have the autocorrelation of U prime, and we plot it against the span-wide separation distance. And you can see it becomes negative, always becomes negative at some point. And then if we plot it and against the average in time block that we do, and you can see when it's negative, actually, for the current canopy, they are all concentrated. The most negative values, so these circles, they almost always happen when the average in time block is around this integral time scale. And for CHETS canopy, the new simulation that my student did, it was not as good as the current canopy, but it's still not bad. So this kind of further confirms our hypothesis kind of does make sense. And with this, we're going to move on to the verification of the second hypothesis, is that now we have stable stratification, and we do expect to see the most negative autocorrelation of U prime, and from the neutral one, we know we need to focus on this red curve. We want to focus on the red curve in each panel, and we expect it to be most negative now at half of the buoyancy period, which is this magenta vertical line, as opposed to the integral timescale, which is this a dotted vertical line. And what we can see is that when the critical wave number is smaller than twice of the integral length scale, which are these 5 panels on the right, we do see that expectation to happen in 4 of the 5 cases, with only this one, f.m, period f.m, to be the only exceptional. And interestingly, that we also, from the lidar images, we also don't see any wave motion during this time period. So our sonic-anemometer data didn't show anything. LiDAR image also didn't see anything. So that's kind of still agreement. But unfortunately for this 4, that we do see what we want to see, the LiDAR was down at that during those periods, and we don't have LiDAR image. LiDAR was not in operation. And for the for another period that we found, we see that the critical wavelength is greater than twice of the integral length scale. And now we see that the most negative autocorrelation of this red line happens actually somewhere between this magenta vertical line, that is the half of the Boyne's period, and the dotted vertical line, which is the integral time scale. So that's also within our expectation. Okay, and now I just want to give a summary of what we have found. Is that we look for signals in sonic-anemometer data, and we focus on the autocorrelation of time block averaged U prime. That's the velocity component fluctuation along the mean wind direction. And we are most interested, we found that we're most interested in the spatial separation on the array, and the sensors were separated by, like, it has the largest separation on the array. It was 13.7 meter, and that was the kind of in our panels, those are all the red lines. And then we found that we look at neutral case and the stable case. In the near neutral case, we see that this autocorrelation at this separation distance will become most negative when we average U prime over blocks of integral time scale. And not only from that one period we found during chats, but also from large-eddy simulation results. And for a stable period, we expect it to be like a mixture of turbulence and waves. And turbulence, by definition, they are dynamically unstable. Waves, by definition, they are dynamically stable. And we expect them to be separated by this critical wavelengths given by Kelvin-Helmholtz instability analysis. And then, and by definition, this wavelength should be larger than the wavelengths of the fastest growing mode of linear stability analysis. And when this critical wavelength is smaller than the average size of these hairpin vortices, that's twice of the integral length scale, and we'll say these hairpins become dynamically stable. And therefore, we find the most negative autocorrelation of U prime when we average them over half of the buoyancy period. So, and they only occur when this wavelength becomes smaller than twice of the integral length scale. That means you need to have sufficiently stable stratification. And that actually explains the second question we originally had from like, by thinking of those like previous papers. And if this critical wavelength is still larger than twice of the integral length scale, then these energy-containing hairpins, they're still dynamically unstable, at least partially dynamically unstable. And then we see that the autocorrelation of U prime at this separation distance is most negative when we average U prime, block average it at some scale that is between the integral time scale and the half the buoyancy period. So for all this, we found actually everything sounds consistent with our expectation. However, when we look back, we actually just get more questions. Yeah, so I think this is kind of the nature of research. You think you answer questions, and then in the end, you think back and you see more questions. So one question is that, we don't really have good cross-validation from different observational data. So for example, these were what we quoted from the paper. And what you can see is like the top one was from Shanmayer's paper. And basically they're saying they got the wave periods calculated using lidar images and the wave periods calculated using sonic-anemometer data. They are not correlated. Like they're always on the same order of magnitude, kind of seems agree with each other overall, but not quite correlated. And then they try to blame the uncertainty in estimating wave periods during, they say, such dynamic conditions. That means the ambient conditions are always changing. And some waves only appear for like 3 minutes. And it's changing so rapidly, like we cannot really do good analysis of measurement data. And then in our recent paper, we were like, okay, we spent a lot of time trying to look for statistically stationary periods. And then we thought we're going to get something, and we did get something. However, when we look back on the LiDAR, it was down. Yeah, it was not working. The LiDAR was down those days. And then we were thinking like, okay, then what shall we do next? Of course, we can go back to the field and just hope we're going to be lucky enough that these sensors would all work when we observe these things. But I'm also thinking about it's more cost effective if we can do large-eddy simulation and to try to see whether this phenomenon they also occur in numerical simulation. I think for me, at least for me, I think it's kind of a more cost-effective way. And another knowledge gap is that, so you see that for our paper, what we did was we just used the Kelvin-Helmholtz instability from the textbook. It was the traditional one. And we just have the mean shear and mean stratification from measurements put into it and then get estimate. However, you can see from that 2023 paper that if you tune this eddy diffusivity, whatever parameters, the result of their fastest growing mode wavelengths can change a lot. And the fastest growing mode and also the critical the wavelengths, they both are outcome from instability analysis. And then if we tune those parameters, it's very likely our critical wavelength prediction will also change, right? And I would not claim that what we did in our recent paper is the perfect one. So there are uncertainties. However, we cannot measure all these eddy diffusivity coefficients in the field, and marrying drag coefficient, heat transfer coefficient, also not quite straightforward, just purely based on measurements. And in their 2023 paper, they were saying, we assume all these eddy diffusivity coefficients are constant, are a single constant. Basically, they're saying Prandtl number is 1, but then you look at their figure, blue curve is the coefficient for momentum, red one is for heat. They're definitely not the same. And also, by making them all one constant, it also say your turbulence is isotropic. And I know because I did this large-eddy simulation, and also the symbols are from measurements. Sigma U, sigma V, sigma W, they are so different. It's not isotropic. So with and therefore, we really want to get a better estimate of these parameters. And we cannot measure all of them in the field. So numerical simulation will be very valuable in this sense as well. So this comes to our future work that I would like to do. do the large-eddy simulation of these stable canopy flows. And it is doable, first I want to say, because we just look at the wavelengths of those nighttime canopy waves. They're on the same order of integral length scale of turbulence. So if we do resolve turbulence well, we're going to resolve those waves well. We're going to resolve their interactions well. So it's kind of doable. And also, advantage is that if you have a canopy, right, and if you're in a canopy-shear-layer, the turbulence length scale is actually larger than if you don't have the canopy. You go all the way down, like close to the ground, and we're getting close to the surface. Those turbulence eddies, their size become very small, and the LES always has kind of difficulty there. And then we need to think about how stable stratification is going to affect our subgrid scale motion. That's challenging, yeah. So, but for canopy flow, we kind of can bypass that because those subgrid scale motions, if they're small enough, they're still unstable. We don't need to worry about them. And then the code we're thinking about is to use the anchor LES because NET has the code that has the explicit representation of momentum and heat exchange between canopy elements and the airflows. It has radial transfer through the canopy. It has energy budget on those surfaces of leaves and those things. So the physical processes we have are in that code. And then we also need to think about how to analyze our LES results. For example, the lidar images say there are those parallel bands of aerosol backscatter intensity. I'm thinking about it's possible we can borrow something that the shallow convection community they actually have. And because horizontal convective rows are these quasi-linear structures. If these parallel bands are also quasi-linear structures, I think there is kind of possibility we can adopt those methods. Okay, and finally, I just want to thank the funding support, the IT support. So some of the preliminary exercising of this stationarity test was actually done by a former graduate student in the statistical department at Penn State. And that was the first time I tried to train a student to do it. And I gathered a lot of experience from that. And then also, I want to thank Anchor EOL for providing access to CHATS data. Stephen Ankley has given us a lot of help. And also the host of CHATS, and also Tasha and Colin. Colin was also an ASP postdoc here. Yeah, his office is right now next door to mine. Yeah, and they were on the committee of that former master students. They gave very valuable feedback to his master thesis. And also this paper published on JES. We want to thank the editor and the reviewers. And that's all for what I would like to share, and I would be happy to answer questions. Thank you so much.
Great. Thank you. No time for questions?
Throw it.
I could. You go back there.
It seems you define the integral scale as the minimum, the negative, in the autocorrelation function, but the definition I'm familiar with is the integral of the autocorrelation function. So how are they related?
Oh, thank you for this clarification. So the integral timescale I plotted here was calculated using the temporal autocorrelation function. They were just plotted here, and it's just a code, it just to say this negative spatial autocorrelation just become most negative at the exact same point.
At the same point as the integral.
Yeah, so we plot this without pre-assuming where the integral timescale is.
Yeah, okay.
And we plot the integral timescale on top of it, and we show it's actually at this point.
Oh, okay.
Yeah, that's a verification of our hypothesis, the hypothesis number 1.
Okay.
Okay. I'll throw this on.
Every time I catch this thing, I'm expecting it to be heavier than it is. I'm just curious about a clarification on the top 2 plots on this one. You show, I think it's a radial distance normalized by either h or r0. Is h the canopy height, or is it like a offset?
Oh, okay.
Or
Yeah, thank you for asking this question. I rushed a little bit through this slide because I was kind of, a little bit in short of time when I went through this. So I only went through this panel. This was like, this h is canopy height. Yeah, so it shows basically it's most negative at approximately like 2 canopy heights. That's kind of consistent with our understanding of the span-wise integral length scale of these structures. And then because it's 1 when r is 0, right? It has to be 1, and it's negative at some point. It will cross 0 at somewhere in between. And this 0 crossing, we call it R0. So for each of the data set, it crosses 0 at some point, and we can determine an R sub 0. And then we can see that if you look at the left panel, different canopy, they are not exactly the same, right? They cross 0 at different points, they become negative at different points. But if we normalize everything by R sub 0, so by its 0 crossing, because 0 crossing is kind of also a measure of how large this lag is. And it's interesting that they all kind of collapse onto each other, yeah. This kind of a confirmation say this is the lag of hairpin, yeah.
Thank you.
Ying, I was curious, did you try to use, to interpret these results in terms of spectra? Okay, because there's a scale at which there'll be overturns, and then all the ones larger than that, there won't be overturns. I wonder if that's related to your buoyancy scales, et cetera.
I'm not quite sure whether I'm familiar with what the results you were referring to. Could you kind of elaborate a little bit more?
Fui, I'd have to look at my at the paper from 2016, but in terms of I'll get back to you. Okay.
Okay. Yeah, it may be easier if I see the paper. Yeah. Maybe Ned can answer this question. I don't know.
No, it's just I'm wondering whether you can more easily define those scales using spectra as opposed to the autocorrelations.
Oh, I see what you meant. I think that's a great question. I think the I am not sure because the reason why we tried to use autocorrelation was kind of they started from here. Yeah, they started from what we saw from the wind tunnel measurements and also from John Finnegan's paper, I think. So spectrum, I think if we're thinking about one-dimensional spectrum, we actually have some limitations when we go to integral scale or larger scale because the energy in the other 2 directions will be aliased to the one-dimensional spectrum. But maybe you are talking about possibly, I don't know whether 2-dimensional spectrum will be possible in this case because it's just so anisotropic in the 2 horizontal directions. So I don't have a quick answer for that, yeah.
I've got a question about the the campaign, and this is a little bit related to the picture you showed. You mentioned Chats was in a walnut orchard, I
Right.
think. So the trees are all lined up in a certain direction. Does that matter then when it's aligned with the mean wind? Like, how do you actually define the? Because that would affect, I guess, the definition of the canopy height. I don't know, like, how much spacing there is in between these rows, or the fact versus a canopy that might be just more kind of heterogeneously or randomly oriented, or sorry, randomly distributed trees.
I think they definitely will have a difference. And that is also the reason why we hope we can do more field campaign. But I go, yeah. So, but right now, Chats kind of is the only data set that I am aware of that we have both tower and horizontal arrays, so we can have separation in both zonal and meridional direction, and can kind of and also has those lidar images, and we like kind of everything can come together. Yeah. To answer your specific question of what the canopy looks like, so the trees are planted 7 meters apart from each other in both zonal and meridional directions. So both west, east, and south, north direction. However, it does not mean they look the same in these two directions because they're going to prune the trees. I think they prune this south-north row this year. The next year they prune this row, and the next year they prune that row. Yeah. So even for where our the towers are located at, the left side and right side, they're a little bit different.
Thanks. Do we have any other questions? All right. If not, let's thank Ying one more time.
Thank you so much.